Hello everyone. So in this video, what we will do is we will solve some more problems on Fourier sine and cosine transformation. So I've already written a problem here. So you see that what I want to do was I want to find the Fourier cosine transform of e to the power minus a square x square, and hence I want to evaluate Fourier sine transform of x into e to the power minus a square x square. So how do you do this problem? Yeah. So one small trick that I'm going to utilize in this particular problem um, from what I already know. Okay. Yeah, let's go through it and then we will understand what is the trick that I'm using here. So what is the Fourier cosine transform of it? Fourier cosine transform of e to the power. Let me write this as simply f of x, and we'll first define f of x as e to the power minus a square x square. So I can write fc of f of x. So that is equal to square root of 2 by pi into integral 0 to infinity f of x into cos sx dx. Now this is going to be equal to square root of 2 by pi into integral 0 to infinity e to the power minus a square x square into cos sx into dx. So that's the integration. Now how are we going to handle this? First things first, what I'm going to do is I'm going to identify what is this function here. I'm going to change this integral to minus infinity plus infinity because I know the well-known formula in that process. You see that e to the power minus x square a square x square, which is an even function, and you see that cos sx, which is also an even function, and hence together it's an even function. That means I can write this particular expression as square root of 2 by pi into 1 divided by 2 times, meaning you can think of this as multiply and divide by 2. So the 2 times 0 to infinity integral of an even function can be written as 1 by 2 times integral minus infinity to plus infinity e to the power minus a square x square cos sx into dx. Okay, good. Now, how are we going to solve this problem? Now, I'm going to solve this problem in a slightly different fashion. So the approach that I'm going to take here is, since e to the power minus a square x square has been there, all that I'm going to do is I'm going to convert this cos sx into e to the power something. You already have that idea. What is that idea? Idea is simple. What is my cos sx? Cos sx can be written as e to the power isx plus not e to the power ix. So this is I can think of this as real part of cos sx plus I sin sx, correct? Meaning I convert this as a complex number and hence I'll took the real part of it, and that is nothing but my cos sx, and that further is nothing but real part of e to the power isx. Now since integration and real part all of them go very well, I can write this as integral square root of 2 pi. Maybe I can write this as, I can cancel this root 2 and this, and therefore 1 by root 2 pi into real part of integral minus infinity to infinity e to the power minus a square x square into cos sx, which is real part of e to the power isx. Remember, I took the real part outside here, and therefore this is e to the power isx into dx. Note that whatever I have done here is going to be valid because I can take this, I can just look at this e to the power minus a square x square, which is a real number. So real number times any complex numbers is going to give you real number times real part plus real number times complex part, and hence taking the real part for complex number then multiplying by a real number is same as that of taking the real part of the complex number which has already been multiplied by a real number. And I also can take this outside from an integration. You can imagine that you can do that by sum, right? For example, if you have two numbers x plus iy, meaning x1 plus i1 plus x2 plus iy2. Now if I want the real part of this together, then all that I can do is I can take the real part of each of them and then sum it up either, or you can sum this up and then find the real part. So here what we do here is we sum this up first, then take the real part of it, which is same as that of what we achieve or what we want. So that's how it works. Okay, because integration is somewhere in fact exactly similar to the summation that what we use in discrete. So here this is 1 divided by square root of pi, real part of this integration. What is this? This is integral minus infinity to infinity e to the power minus a square x square plus isx into dx. Okay, fine. Now you got the idea. So what we have here is e to the power something, and that something probably can be written as a linear term and its square, and hence I can do some substitutions and then get the answer. That's the idea. Okay. Okay. So now you can complete the square here. So 1 divided by square root of 2 pi into real part of actually integral minus infinity to plus infinity e to the power. Let's take this into rough side, minus a square x square plus isx, which can be written as minus a square x square. Then in fact I take this x minus a square outside, therefore this will give you minus a square times x square plus isx by a square, right? S square minus isx by a square. So therefore this one is minus isx by a square, and hence this is going to be minus a square times. Now let's complete the square. So here you have a square, here you have minus 2ab as well, and hence the b term that we were looking at is nothing but is by 2a square, correct? So this is is by 2a square, because it's supposed to be 2ab, so multiply and divide by 2. So here it is x minus is by 2a square whole square, and you also have to subtract what you have added, which is a square divided by 4a square with one I, which is I square, therefore I get minus 1 here. Okay. That's the idea. I'm sorry, so subtracted one has been actually added, and then the added one has been left out. So therefore this particular term in the top in the exponential can be written this fashion. So therefore this is going to be e to the power minus a square times x minus is by 2a square whole square minus a square by 4a square into dx. So that's the problem. Okay. So now what we'll do? Now use the substitution method and solve this problem. You see, what is the substitution that we will try to do it? If you want, you can also probably write this integration itself in terms of d of x minus is divided by a square whole square, and hence you can figure it out. But I think that become a little bit, that might expect you to understand a little bit more. So what I will do is I will do a small simple aspect of it. I will say let u is equal to a into x minus is divided by a square, and hence you will complete the substitution. I think 2a square, yes, x minus is divided by 2a square. So this will give you, of course, du is equal to dx. I think so, dA dx, because a is outside. Therefore this will give you dx is 1 by a times du. So substitute all of them together. So therefore this will give you, obviously remember the limit does not change, because as long as u goes to infinity, s goes to infinity, u goes to infinity, x goes to minus infinity, u goes to minus infinity. So the limit does not change. So integral 1 divided by square root of 2 pi into real part of integral. Now this time this is u is equal to minus infinity plus infinity e to the power. Now what is the substitution? Substitution is u equal to a into x minus is, right? Substitute that and should get e to the power minus u square, and the other term is e to the power minus s square divided by 4a square, correct, into du. Now you see that e to the power minus s square divided by 4a square is completely a constant term, so I can pull it out. So in fact, I can pull it out from the real part as well because it's a real number as well. So e to the power minus a square by 4a square divided by square root of 2 pi into real part of this integral minus infinity to plus infinity e to the power minus u square into du. Have you noticed this integral somewhere? What is this integral? Did I miss 1 by a somewhere? Yeah, here. It's supposed to be 1 by a here. So therefore a can be taken outside. Now what is this e to the power u minus u square into du from minus infinity to plus infinity, which is square root of pi. So that's the standard result. So therefore this is equal to e to the power minus s square divided by 4a square divided by a into square root of 2 pi into square root of pi, its real part, which is square root of pi itself, right? Because real part of a real number is the same number. So that will get cancelled with this pi here, and hence what we will get as an answer is simply 1 divided by a into square root of 2 into e to the power minus a square by 4a square. So that's my Fourier cosine transform of e to the power minus a square into s square. Okay, fine. Now what we wanted was, we wanted to find Fourier. What was the question? Yeah. The question was, and hence evaluate the Fourier sine transform of x into e to the power minus a square into x square. Now we have seen this somewhere else. Can you remember what was that? The Fourier sine transform of x into something is nothing but the differentiation of Fourier cosine transformation, correct? Of course, with the minus. So how do you do that? So let me write here. So by property, I think it is written in the property number 4, I guess. Check that. So by property 4, what we know is, we know that the Fourier, meaning suppose if you differentiate Fourier cosine transform of f of x, what you're going to get is the minus of Fourier sine transform of x into f of x. So all that I wanted was this right hand side, which is listed over there. So this implies the Fourier sine transform of x into f of x, which is what I wanted, is actually equal to minus d by ds of the Fourier cosine transform of f. Okay. Therefore, this is going to be equal to minus d by ds of what was the Fourier sine transform, cosine transform, which is this, right? So a by root 2 times integral e to the power minus a square by 4a square. So this is 1 by a root 2 into e to the power minus a square by 4a square. And who's this fellow? Of course, complete this integration, complete the differentiation, you should get s into e to the power minus a square by 2. Okay. Yeah. So that's all for this problem. I think I made a mistake. So this is not what I meant. The answer was square root of 2s divided by 4a cube into e to the power minus s square divided by 4a square, right? Remember, see, this differentiation is easy enough. 1 by a root 2 can be taken outside because it's a constant, and minus retains. E to the power minus a square into a to the power minus a square by 4a square has to be differentiated, which is e to the power minus a square into 4a square times the differentiation of the numerator, which is differentiation of the exponential term, which is 1 by 4a square times minus 2s. Okay, and then minus and minus gets cancelled, and then 4 and 2 gets cancelled like this, and then 2 and square root of 2 will get cancelled. Therefore, altogether it gives you square root of 2 into s divided by 4a square, 4a cube into e to the power minus a square divided by a square. Okay, fine. Now, as probably an exercise, what you also do is you solve, meaning you continue this problem, and then find out, and hence it seems like hold on guys, it seems like I made a small mistake. Yeah, correct. What I wanted was Fourier sine transform of x into f of x, correct? And that is, yeah. Let me just check whether I have written the question properly. Fourier sine transform of x into f of x, that's what I wanted. And I found Fourier sine transform of x into f of x. Okay. So now you can continue this. So, and hence evaluate. Remember, you also can evaluate Fourier cosine transform, right? Yeah, x into Fourier cosine transform of x into f of x also you can find out. Write the problem. And hence evaluate Fourier sine transform of x into e to the power minus x square. Right? You're just substituting a equal to some appropriate. That's all. All right, guys. Solve the more problems on the same thing, and I'll see you in the next video, which we will talk about something called convolution theorem, and after that we will talk about evaluation of the integrals as well. All right. Thank you, guys. See you in the next lecture.